so our next speaker is Quang. So we're going to continue our transport plan talks. Looking forward to your talk.
Thank you very much. So first of all, I would like to thank the organizers for organizing this wonderful event, especially for the EPFL team. So merci beaucoup. So the title of my talk, the geometry of Gaussian measures and Gaussian processes via information geometry and optimal transport. So I would talk about both kind of the information geometric aspects and then the optimal transport aspects. So the talk will be very concrete because I will focus on the Gaussian setting. So it's a lot more concrete than the abstract setting, the highly abstract setting that Lina-Ik was talking about just now. So thank you for introducing all the optimal transport notations and formulations, so I wouldn't not have to talk too much about it. So I wouldn't basically, so the research team that we have been focusing on is on the machine learning and statistical methodologies using functional analysis and geometrical methods. So we use Hilbert space and finite space theories, and in particular the theory of the methodology of reproducing Hilbert spaces, so RKHS. And we use like matrix and operator theory and Riemannian geometry, information geometry and optimal transport, etc. So as I said, I will be focusing on a very concrete setting. So I would like to generalize the following geometrical structures for Gaussian measures in Rn to the infinite dimensional setting of Gaussian measures on Hilbert space and Gaussian processes, because we have for Gaussian processes we have underlying infinite dimensional Gaussian measures. So we have so there are a lot of geometrical structures for these objects. We have Riemannian matrix and distances. We have optimal transport distances. We have the divergences, and people are also studying kind of the connections and unifying formulations. So there's a very rich literature on these objects. So the kind of the mathematical theories and techniques that we're using are operator theory, especially positive definite operators, and Riemannian geometry and Gaussian measures in the infinite dimensional setting. Now, so of course we are just focusing. I'm talking some big words here, but we are focusing on the very specific case of the Gaussian measures. So the motivations for studying this for the geometrical structures of Gaussian measures and SPD or symmetric positive definite matrices, they have not just like they play a central role, of course, in probability and statistics, in machine learning, but they also have a lot of practical applications. So there are numerous applications in brain imaging, in computer vision, in radio signal processing, in brain-computer interfaces, where they use these objects as a form of data representation. So we have one of our speakers here, Tomek. We were talking about like kind of these brain-computer interfaces, I think. So okay, so one of the this object is from information geometry. It's the Fisher-Rao metric. So and the corresponding something called the affine invariant Riemannian metric for the set of SPD matrices of size n by n. So this is it has been studied extensively. So let's consider the setup. For this, in this talk, I will just focus on the zero mean Gaussian measures. So for the setup, zero mean Gaussian densities on Rn, they are completely characterized by their covariance matrix. And so I think this one can be used for pointing, right? Yeah. So it's completely characterized by the covariance matrix sigma here, and so because of the symmetry, if we have like n times. If we have n by n matrix, and we can represent it by n times n plus 1 over 2 kind of parameters. And so we have so this we can consider this set as kind of a smooth manifold, and we on it we can define something called the Fisher information matrix. So it's given by this formula here. This is a classical central object in statistics, and it was introduced by Fisher a long time ago, like 100 years ago. Has a lot of important roles in statistics. And it was Rao in the 1940s actually kind of first one to consider it as a Riemannian metric on the setup Gaussian density with zero mean. So just to say that, so Fisher introduced this like 100 years ago, and Rao introduced this in the 1940s. And just a small note, kind of for curiosity, Rao is still alive, believe it or not, 102 years old. Oh. And I think he's still doing research. He's still active actually. 102 years old. He's now in the US. So this Fisher-Rao metric is a central element in information geometry and started by Amari. And so for the in the Gaussian setting, we can compute it explicitly. This is a very nice thing about the Gaussian setting because we can compute many things explicitly. And so in that setting, we can compute this the Fisher information matrix explicitly. And this is just differentiating with respect to the parameter theta I. And since we have the correspondence of the Gaussian densities and the covariance matrices, so we have the corresponding kind of something called the affine invariant Riemannian matrix on the set of SPD matrices such n by n. And so the Riemannian matrix is given by this formula here. And it's called affine invariant because we transform A, for example, by like C times A times C transpose, and the same for B and sigma, then everything here remains the same. And so this object has been studied a lot. I can trace this as far as also like as far as back in the 1940s. So under this matrix, we have a Riemannian manifold, and we have a unique geodesic joining any two matrices A and B, given by this formula here. So it's an explicit formula. And the Riemannian distance also has a closed form formula. So it has a lot of structures that can be computed explicitly and corresponding to the Fisher-Rao distance between zero mean Gaussian densities, such as the Gaussian densities on Rn. And a simpler form is something called the Laplacian matrix. So here we have the Laplacian matrix motivated by the setting of a brain division tensor imaging in brain imaging. It's simpler to compute than the previous metric. So this one, the geodesic has a simple form, and it has the Riemannian distance also has a simple form, and it's faster to compute than the previous distance. And under this metric, this manifold is actually flat, so we can use it to define positive definite kernel such as the Gaussian kernel. So this is a valid positive definite kernel. It's not the case with the previous distance because it can be shown that if the manifold is not flat, so the previous manifold is a Cartan-Hadamard manifold, so it has negative curvature. And it can be shown that if we define the Gaussian kernel with the distance, that Riemannian distance, then it's not always positive definite for every bandwidth of the kernel. So this one is always, we can always define the Gaussian kernel. So these two have been applied quite a lot. And so those are kind of like the two Riemannian structures. And this one is, we also have something more, like the divergences. So this one is called the log-determinant divergences. So the alpha log-determinant divergence is parameterized by a parameter alpha here. So these generally they do not correspond to metric distance because they're not symmetric. It's symmetric if only if alpha is equal to 0, so alpha equal to 1, and negative 1, we have the limiting cases. And this corresponds to the Rodinet and Kullback-Leibler divergences between zero mean Gaussian densities on Rn. And so these have also been used a lot. So for example, in the case of the Quang divergence, or also like the relative entropy, and the word for it is relative entropy, we have it corresponds to the case when alpha is equal to 1. And in general, we have the Rodinet divergences when we have correspond to the log rate when alpha is equal to like 2r minus 1 here. So these are some of the things that have been studied a lot in the finite dimensional setting. And now we have the optimal transport. Let's consider the optimal transport distances. So very briefly, because Lennart was talking about just now, so I'm going to consider the optimization, like the optimal transport between two populated measures nu0 and nu1 on a set x, let's say x equal to Rn, with a cos function c. I would just consider c equal to the square cos, and so we optimize this expected value of the cos function cxy, where gamma is the joint probability distribution between nu0 and nu1. And so in the case of the finite moment probability measures, finite moment out of P, then we have something called the P plus time distance, which takes the 1 over P root of this quantity here and defines the metric on the set. And so it has been studied, of course, extensively. And so as I said, I would just focus on the Gaussian setting. So in the Gaussian setting, two Gaussian distributions with the square cos function, then it has a closed form formula, and it has been worked out by various authors before in various like in the 1980s. And it has a nice closed form formula. In the case when the mean is equal to 0, we also have this formula. It's called the Boris versus time distance. And this distance is used in quantum information theory for characterizing the kind of the similarity between quantum states. And so the nice thing about this distance is that it's always well defined when if C0 and C1 are singular. Because for the previous like distance and divergence, we have to compute the inverse and the log and so on. So everything has to be strictly positive definite. It's not the case with this one. So the Wasserstein distance is always well defined, even if C0 and C1 is equal to 0, for example, it's still well defined. So that is one very nice property of the Wasserstein distance. always well defined. And another very nice property is actually now if we move to the setting of infinite dimensional Gaussian measures of a Hilbert space, the formula remains the same, which is not the case with the previous distance and divergence. They only well defined in very specific setting. Whereas this is still, they always well defined. And so there have been some recent work on applying these Gaussian processes recently. And so it's valid in the case when 0 is 1 are singular as well. One thing that is one thing that is not too good is actually it's not partially differentiable because we have the square root here. So when we differentiate, for example, like informally, we take a square, we divide by the square root, so then it's not differentiable. It's kind of unbounded. So I will come back to this a little bit later on. So let's move to the entropic regularization. So thank you was also talking about this. So as we have just heard, the exact optimal transport distance is actually not just like analytically computationally demanding, but like analytically difficult, but also computationally generally demanding, and can have very bad sample complexity as well. So it can be, the worst case can be exponentially bad. And so for the entropic regularization, we add this also. Lindeck was using kind of the relative entropy kind of notation of this scale divergence of the same thing between gamma and the product measure mu. And so this allows a much faster, like there are algorithms to solve it faster. And of course, it's by adding this regularization term, we have a bias. So this one is not equal to 0 because mu is not equal to 0. So there's a notion of de-biasing. So it comes to synchron divergence. So we subtract these two terms here. So it becomes like a valid divergence. So there has been a lot of work on studying this entropic regularization and synchron divergence. So let's consider the case of the Gaussian setting. Let's say on Rn. So here, so the formulation has been worked out a couple of years ago. So we can represent this quantity's mutual information by the differential entropy, and this is the differential entropy here. And so we have this property called the maximum entropy of Gaussian density. So if X is mean 0 and covariance matrix C, then the differential entropy is maximum if X is Gaussian. So if mu 0 and mu1 are both Gaussian, and we want to minimize this whole thing, then the minimizer has to be Gaussian, because gamma has to be Gaussian. So if we use that, the maximum, so the key here is the maximum entropy of Gaussian densities. So the minimizer here has to be Gaussian, the gamma here has to be Gaussian, and it has to have this form here, where C here is a cross covariance matrix. So we have to optimize over C. And so we can have this scale divergence, or the mutual information is given in this explicit form. So we can just plug this in and optimize, and we can obtain a like explicit. This is the formula. So this is for the OT epsilon, and this is for the synchron divergence, where we subtract like the kind of the bias terms. So this is the finite dimensional setting. Now, so we can generalize this to the infinite dimensional setting, but we have to be careful because the entropy here, this is the formula for the entropy. Now, this is not well defined in the infinite dimensional setting because we have in this case, we have if we have a covariance operator C, it has infinitely many eigenvalues that go to 0, always go to 0. And so this is not well defined. However, and then, if we look at the joint measure for gamma, for example, two measures, nu0 and nu1, then this is the formula in the finite dimensional setting. This on the right-hand side here is not well defined, but the left-hand side is well defined. This mutual information is well defined. It can be infinite, but it's well defined. So the correct generalization of the maximum entropy property of Gaussian densities on Rn to the infinite dimensional setting is not the maximum entropy. It's the minimum mutual information. So if gamma and gamma 0 are two joint measures of two Gaussian measures mu x and mu y with the same covariance operator gamma, then this quantity here is minimum if and only if gamma is equal to gamma 0. It has to be a Gaussian, and it's given by this form here. It's an explicit formula. Well, this one here is called the Fredholm determinant, so it's kind of the identity minus like a just class operator. So this V here is kind of links the covariance operator of the product measure of x and y with the covariance operator gamma. So we can plug this formula in. So it means that the minimum of this expression in the infinite dimensional setting has also be a Gaussian. And so we can plug the formula here for the KL divergence, and we can solve for this as well. Now this is an infinite dimensional optimization problem, but it can also be solved, and it has the closed form formula, so we can obtain the closed form formula. Another way to solve it is we can solve it via the Schrodinger system. Something called the Schrodinger system that we can solve for the predominant Euclidean density of gamma with respect to mu0 and mu1, so we can obtain a closed form formula. So this is the closed form formula. It's actually the same as the finite dimensional setting. We have to be very careful here because this is something called the Fredholm determinant. So it has to have this form, like identity plus a trace class operator. So it has to be in this form, but it's well defined. And when epsilon go to 0, we obtain the exact versus time distance. And then when epsilon go to infinity, we just have the kind of the square of the mean. And so now, so what are the properties of the synchron versus the exact, the entropic regularized versus the exact versus time distance? So many properties actually become very clear and very distinct in the infinite dimensional setting, and not so clear in the finite dimensional setting, but very clear in the infinite dimensional setting. So first of all, they are both very well, both the exact versus time distance and the synchron divergence are always well defined and finite, including the setting for singular covariance operators. Whereas the compact library divergence and the range divergence are only finite if the Gaussian measures are equivalent. So in the infinite dimensional setting, in the finite dimensional setting, the two Gaussian densities are always equivalent. They have the same support with the full support of all the whole Euclidean space. For Hilbert space, this is not the case. They are either mutually equivalent, so they have the same support, or they're disjoint under very specific conditions. So these quantities are defined. The divergence, KL divergence, for example, is finite if you only the Gaussian measures are equivalent. So now the synchron divergence has many nice properties. So it's differentiable because we have this kind of regularization, so it's special differentiable. The versus time distance is not differentiable in infinite dimension. So methods such as the gradient descent can be employed for the synchron divergence, but not theoretically not valid for the versus time distance. Now, I'm not going to talk about I don't have the kind of the details for the barycenter problem here. So when Lynette was talking a lot about the barycenter, I don't have the slides here, but I can say that the barycenter is much better behaved. The problem is much better behaved. It always has a unique search valid both in a singular setting. Now, for the finite, for the exact versus time distance for the Gaussian, and in the kind of the equation for the finite dimensional setting, the analysis for it doesn't really extend to the infinite dimensional setting because often we require that we assume that it's only valid for the case when all the covariance metrics are strictly positive, and in the kind of the standard proof, we assume that all of them are greater than the identity multiplies by a constant. Now that analysis doesn't extend to the infinite dimensional setting because we cannot assume that a covariance operator is greater than the identity operator multiplied by a constant. That's not valid. Whereas, oh, what did I do? What happened? Whereas for the synchron divergence, I think what happened? Huh? Did I click on something? Is something unplugged? Did I click on something wrong?
I think you should be.
Sorry. Okay, what happened? Sorry. Okay. Whereas for the okay, I was just saying that for the synchron divergence, the barycenter always there's always a unique solution valid in both the singular and non-singular settings. So it's and for the so I'm talking about the convergence of the sample complexity. So it's very well known that the versus time distance is it corresponds, the convergence of the versus time distance corresponds to the weak convergence. So if we have a sequence of Gaussian measures with covariance operators A and A, then they converge in the versus time distance even only if the covariance operator converges in the trace class norm. So this result has been known for a while now, many years. Whereas for the synchron divergence, we have the convergence if the covariance operator converges to the Hilbert-Schmidt norm. This is at the moment it's an if statement. It's not if and only if. Maybe it's if and only if. So the consequence of this, so this is a trace class. This is a sum of all the eigenvalues, the absolute value of all the eigenvalues. So the L1 norm, and this one is an L2 norm, the sum of all the eigenvalues square. And so it's a Hilbert space norm, and then we can apply laws of large number of Hilbert space value random variables to obtain sample complexity. Now it's okay. So just to summarize, this is the Hilbert space norm convergence, whereas Whereas for the Wasserstein distance, it's a trace class norm. And so we can use like the law of large numbers for finite space value random variables to obtain almost sure convergence. I will go into this into the next few slides, but it's harder to obtain rate of convergence in infinite dimension. Okay, so I probably will just talk about this setting. So now let's, because also the formulas before, they are all kind of abstract Hilbert space formulas. So the operators are all abstract Hilbert space operators. So let's talk about a setting where we can actually estimate these distances and divergences in a concrete setting of the Gaussian processes. So let's assume that we have P. Here's a nice metric space, such as interval from 0 to 1, and nu is a nice measures on T, such as the Lebesgue measure on, let's just say the interval from 0 to 1. And consider the Gaussian process with mean function MP and covariance function KST. So I will assume that the sample paths are all square integrable. So there's a one-to-one correspondence between this Gaussian process's square integrable paths and the Gaussian measures on the space of the Hilbert space H equal to L2T nu with the covariance operator given by the integral operator with the kernel KST. So this is an example, for example, just an example here. So we have this Gaussian process here with the covariance function. This is the covariance function given by the Laplacian kernel. So it's kind of very wiggly here. And then here we have the Gaussian kernel. So the paths are a lot smoother. So this is the interval from 0 to 1. So they have the underlying, Gaussian infinite dimensional Gaussian measures on the space L2 T nu. So we can compute like the distance between we can compute the distance between the corresponding Gaussian measures on L2 T nu. So that's a lot of work actually studying this distance, the various distances between the Gaussian measures. For there's a lot of work in functional data analysis. So we have the study like Hilbert-Schmidt distance and the work using the Wasserstein distance. And recently there's work in machine learning for the kind of functional Bayesian neural networks, where they so last year, for example, at the nearest last year, they were using kind of Wasserstein distance for the in this context. Now they were actually using gradient descent. As I said before, the Wasserstein distance is actually not differentiable in the infinite dimensional setting. So theoretically, this is not rigorous. We use a Wasserstein distance. Of course, in practice, we use finite dimensional approximation, so we can still get some results. But theoretically, it's not consistent. So now let's so now we would like to be able to compute this distance in the L2 using finite dimensional formula in RM. So if we have really sample like m points, sorry, I take from 1 to small m in T, and we have like we have a vector of size m, which is different, which is distributed according to the finite dimensional Gaussian with the kernel with the covariance matrix given by the kernel matrix Kx. And so we can show that under a certain assumption, we can estimate the infinite dimensional formula using the finite dimensional formula, and we can see the difference between the synchron divergence and the Wasserstein distance. So okay, I won't skip this few slides because it's rather complicated, but I just want to say that this analysis actually uses RKHS because we have two Gaussian processes. Each one has a kernel function, so we have the corresponding kind of RKHS operators corresponding to them. I just want to say that, so this is a result here. If we sample like this SX here, sample independently from T nu, then we can estimate the synchron divergence by the in L2 by the synchron divergence in RM here, and we have a dimensional independent sample complexity depending on the number of sample points, and this is about of the kernel. And so the analysis, as I said, the analysis uses a lot of RKHS covariance and Gauss covariance operators. Because these operators CK here, they are not RKHS operators because they map from L2 to L2. Now there's no, so this is actually very nice, and this is because we use the Hilbert-Schmidt norm convergence of the synchron divergence. It's not the case with the Wasserstein distance. Now, as I said before, the Wasserstein distance converges to the class norm, which is a finite space norm. So at least for the moment, I have to assume that at least one of the RKHS is finite dimensional. So assume that if, for example, HK2 is finite dimensional, then we have like this kind of sample complexity here, but it depends on the dimension of HK2 because of this finite space just class convergence. I'm not quite sure whether this can be improved. At the moment, it's not clear to me whether it can be done. So maybe someone can help me. Maybe Linda can help me. But anyway, so this is the difference between the second difference between the the entropic regularizing convergence and the exact Wasserstein distance. So now the first difference is actually, as I said, the Wasserstein distance is not differentiable in the infinite dimensional setting. The single divergence is differentiable. The second one is this convergence. One is the Wasserstein distance converges in the chess class norm. The single divergence converges in the Hilbert norm. And so we have for the single divergence, we have dimension independent sample complexity, whereas for the Wasserstein distance, we have this at least for the moment is still not yet dimension independent. So okay, we can also so before we assume that kx is known, so we can assume that we can also estimate it from finite samples as well. But basically, I will skip this because it's not so important, just technical. And we can have like a kind of a similar estimate based on the number of sample points t on the interval from 0 to 1, and also the number of sample paths as well. But this is not just a technical part. So I'm gonna illustrate it with okay, so here we have a two Gaussian process here with very similar kind of kernel function. This is a is equal to 1 and a equal to 1.2, so very similar. So this is the, I just consider the t from 0 to 1 to power d, where d is equal to 1 and d equal to 5 and d equal to 50. So the estimation is using n like sample paths for each process, so n from 1 to 1,000. So here we have the Hilbert distance. Here we have the synchron divergence with epsilon equal to 0, 1, and here we have the Wasserstein distance. So the behavior of the synchron divergence and Hilbert distance is quite similar across the different dimension d here, whereas for the Wasserstein distance is different because it's kind of slower when d becomes large. So anyway, so I'm not, okay, so I don't think I have time because I'm running out of time. Maybe I just mentioned it very briefly. So that was the optimal transport with the exact Wasserstein distance and the synchron divergence. So many things can be computed explicitly and analyzed explicitly. So for the information geometric quantities, we have the Fisher-Rao distance and the log-red divergences as well. So these are not directly generalizable to the infinite dimensional setting because these are kind of the inverse. For example, these are only modified in very special settings. Nevertheless, we can, by doing regularization, we can actually generalize this to the highly to the infinite dimensional setting of the Hilbert space, where we can do a form of regularization. So here we, instead of just computing the divergence of the determinant of A, we compute the divergence between A plus gamma I for AB being chess class, for example. And then here this form of the extended formula of the threshold determinant, where we have gamma instead of gamma equal to 1, we can have gamma be greater than 0 for any gamma. Just to say that we're doing regularization as a form of regularization, and then we can use this, we can recover the Quang divergence as well between two Gaussian equivalent Gaussian measures on the Hilbert space. So when gamma goes to 0, we obtain the Quang divergence between two Gaussian measures, equivalent Gaussian measures on the Hilbert space. And it has a closed form formula. So there are, so we can actually generalize all of these, the distances and divergence we talked about just now, to the infinite dimensional thing via regularization, and we can recover the exact quantities in the setting when the Gaussian measures are equivalent. Okay, and we can also define like the regularized Quang divergence, and we can obtain sample complexity as well. Anyway, so and the setting we can also have like a very high general setting of the alpha beta log-red divergences of the Hilbert-Schmidt positive definite Hilbert-Schmidt operator. So we have A plus gamma I, where A is Hilbert-Schmidt operator, and gamma is greater than 0. So then we can, so this encompasses both the alpha log-red divergence and the phi invariant remaining distance. So this setting is actually more general than the Gaussian setting because for the Gaussian setting, the covariance operator is a chess class operator, whereas here we can have like the Hilbert-Schmidt, like positive Hilbert-Schmidt operator. So it's more general than the Gaussian setting. Okay, so okay, I think I'm running out of time a little bit. Just to give you an example here, see, like this is the kind of the regularized Quang divergence, and then you can have the Rayleigh divergence with different order. This is between these two Gaussian processes, and this is where the Gaussian processes are a lot closer to each other, then the quantities are a lot smaller. So we have kind of the convergence here. So to summarize, so we can generalize the many distances and divergences and geometric structures between Gaussian densities of Rn to the Hilbert space setting. So one key technique here is regularization. So for in the entropic setting, we have entropic in the in the optimal transport setting, we have entropic regularization, and that lists of many nice properties of the compared to the exact distance. And in the others, for example, we have a Hilbert-Schmidt norm convergence that lists of dimension independent sample complexities. And for the other quantities, some information geometry quantities we also use regularization, and we also obtain many nice properties as well. So there are a lot more theoretical results can be obtained, and I'm trying to look to obtain like numerical practical regression processes, and of course we have to move beyond the Gaussian process setting. So thank you very much for listening, and I have some references here. So thank you very much for listening.
So thank you for a great talk. So unregularized optimal transport.
Yes.
Still NP hard for Gaussian cases?
Now for Gaussian setting, we can obtain Gaussian formula.
Okay.
So there's no numerical work here actually, because we in the Gaussian setting we obtain everything is analytical here.
Even in finite dimension.
Yeah, because we don't have to do any optimize like numerical optimization here. We don't have to do any computation optimization here actually, because everything here is analytical. Well, except for the very central problems, because the very central problem we may have to be computed numerically, but otherwise all the distances and all the structures are actually we can compute many things explicitly. So that's a good thing about it actually.
Thank you very much.
Thank you for the talk. So when the single divergence regularization parameter goes to 0, we go to Wasserstein distance. But when it goes to plus infinity, so we know in general we converge to some maximum mean discrepancy. What happens for Gaussians? Do we recover some standard notion of distances?
The difference between the means actually the square.
Because you have the square distance cost, so it degenerates.
Mean square,
All right, if there are no other questions, thank you, speaker again.
Thank you very much.